So hello, my name is Harrisson. I'm a researcher at the LCPO laboratory in Bordeaux in France. And I'm going to give a talk as part of the educational workshop organized by the Polymer Education Committee and Macro 2022. And what I want to talk about is to really drill down into the concepts of dispersity, molecular weight distributions, and then finally give an example of how we use those ideas for some applications in self-assembly of amphiphilic polymers. Now, the word polymer comes from the Greek words poly, meaning many, and meros, meaning parts, as we all learned in our undergraduate polymerization lectures. And this is because a polymer consists of many repeating units. But we could also think of these many parts as being the many different molecules that make up a synthetic polymer. Because a synthetic polymer, in virtually all cases, is composed of many, many different molecules, which all have different molecular weights. And in the case of copolymers, we have even more variation because now we have distributions of global composition. We have differences in the way that individual monomers are distributed within the different monomer chains. If we then start to add changes in topology like branching, or the presence of cyclic polymers or star polymers, we have just so many different kinds of distribution. And really, when we look at the history of synthetic polymer chemistry, a lot of it has been about trying to tame this incredible variation in polymer structures. And so we look at the development of anionic polymerization, the living polymerization techniques, or the development of reversible deactivation, radical polymerization techniques. We see that one of the things that we've been chasing has been trying to reduce dispersity, with a particular focus on molecular weight dispersity, as much as possible. And so if we look, for example, over the last 10 years, what we've seen is a real rise in what you might call precision polymerization. And if we focus on precision polymerization done using chain polymerization techniques such as reversible deactivation, radical polymerization, ring opening metathesis polymerization, or ring opening polymerizations, coordination chemistry, and so on, we find that there's been a movement towards ever more complex structures which require a very precise level of control. So we can look at, one of the pioneering authors in this field is Jean-Francois Lutz, who about 10 years ago started working on copolymers which contained different functionalities at quite well-defined regions of the chain, making use of the strong tendency of maleimide to alternate with styrene and a range of different functional maleimides that allowed the introduction of different functionalities. Around the same time, we had Mikey Whitaker, who pioneered the synthesis of multi-block copolymers with a synthesis of a 6-block copolymer using an SET LRP technique. And then this was taken up by other groups such as Sebastian Perrier's group or Dave Haddleton's group at the University of Warwick. And they really pushed that to the production of multi-block copolymers containing 20 or more blocks of different monomers arranged in defined sequences. So really producing quite complex structures. Now, more recently, we started to see the use of dispersity as a parameter in synthesis. So rather than just simply trying to reduce dispersity as much as possible, we've seen people start to try and control dispersity and be able to dial in different dispersities. And so the Anastasaki group, for instance, has done a lot of work in this, and they've developed conditions that allow by, for instance, mixing different raft agents or mixing different initiators in ATRP that allow you to dial in whatever dispersity you want. And they've even taken that to the point where using switchable raft agents, you can make multi-block polymers where each block has a different dispersity. You can, for example, alternate between high dispersity blocks and low dispersity blocks in the same polymer. If we look, for example, at the Force group, they've been looking at controlling the shape of molecular weight distributions. And they've shown that by gradually adding an initiator or a chain transfer agent or a catalyst throughout the polymerization, you can produce molecular weight distributions that skew either to low molecular weights or to high molecular weights. And this has an effect on the different properties of the materials that are produced. And then you can go even further. And so, for example, Tanya Junkers has shown that it's possible to make bespoke distributions of essentially any shape you want by blending different oligomers or different narrow molecular weight polymers to produce a blended distribution that contains whatever different ratio of different molecular weights that you're looking for. And that's been taken even further using flow chemistry, notably by Cyril Boyer and Jiang Zhu, and most recently by Damien Guéronnet, who showed that they could essentially design whatever kind of molecular weight distribution they wanted, and then set up a computer-controlled flow reactor that would sequentially generate a range of different distributions that were then all combined together at the end to produce a molecular weight profile that corresponded to the desired profile that was initially programmed in. And what all of these different techniques have in common is that the concept of molecular weight dispersity and molecular weight distributions is absolutely central to these different techniques. But these concepts are actually not that intuitive, and I think it's really worth taking some time to have a look at what dispersity really is and what molecular weight distributions look like. And what I hope to show in this lecture is that polymer distributions tend to be a lot broader than we imagine, and that when you're looking at copolymers, whether they're block copolymers or random copolymers, you have also distributions of composition that you need to consider too. And so as a result, the chemical structures that we draw greatly oversimplify polymer complexity. So what I want to show in this presentation is basically, I'm going to start by talking about what dispersity is. Then I'll move on to looking at what molecular weight distributions really look like, and talk about composition distributions in the case of multiblock and gradient copolymers, and finish with an application in self-assembly of amphiphilic gradient copolymers, where we've taken some of these concepts about composition distributions and the kind of random variation that's inherent in them in order to generate a simpler structure that mimics a gradient copolymer. So to begin with dispersity, there are actually two kinds of dispersity defined by IUPAC. We have the mass dispersity, DM, which is the ratio between the number average and weight average molecular weight. And we also have the degree of polymerization dispersity, which is, of course, the ratio between number average and weight average degrees of polymerization. And because the mass is related by a very simple relation to the degree of polymerization, in most cases, these are effectively the same thing. So the mass is just equal to the mass of the molecular weight of the monomer multiplied by the degree of polymerization plus the molecular weight of the end groups, as long as the molecular weight of the end groups is small relative to the molecular weight of the polymer. We can ignore them and just treat the dispersity as the mass and the degree of polymerization dispersity as being the same. Now, the number average molecular weight is simply the average molecular weight of all the chains. This is the average that we normally think of when we think of an average. The weight average molecular weight is the average that you would get if you asked every monomer what's the molecular weight of the chain it belongs to. And so the chains with the highest molecular weight get counted more often than the chains with the low molecular weight. And as a result, this average is biased towards the high molecular weight chains. The dispersity is then simply the ratio of the weight average and number average molecular weights. In the example shown here, the dispersity is 1.7. Now, this is useful in that it tells us what the relationship between the weight average and the number average molecular weight is. So we have properties that depend on the weight average molecular weight, such as the amount of light scattering, properties that depend on the number average molecular weight, such as, for instance, if we have polymers with fluorescent end groups, the fluorescence of the polymer, then the dispersity will tell us something about the relationship between these properties, but it's not a very intuitive measure of dispersion in a distribution. It doesn't really tell us anything about the range of molecular weights that we might expect to find in a polymer. And if we wanted to know more about that, we might turn to the kinds of statistical measures that we typically use for distributions, such as the distribution of the heights of people in a room or the distribution of temperatures in a city throughout the year. And that would be the mean and the standard deviation. So the standard deviation essentially just tells you how far on average any given element of the distribution is from the mean. And it's a very intuitive measure because most of the members of a population are going to be within plus or minus 1 standard deviation of the mean. And typically, that's going to be about 70% of the members of the population will be within 1 standard deviation. Now, there is a relationship between standard deviation and dispersity, but it is not at all obvious. And to give you an example of that, I'll show you a sort of sample population. It's a young family consisting of 2 adults, a 4-year-old girl, and a baby. And they have heights which range from 50 centimeters up to about 170 centimeters. The average height is 122 centimeters. The standard deviation, 52 centimeters. So you can see that this is quite a broad distribution. The standard deviation is nearly 50% of the average in this case. So what's the dispersity of this distribution? You'd think it might be quite large. In fact, it's only 1.17. So this is a dispersity. But if you got this in the context of a controlled polymerization, you'd probably think, oh, that's quite good. Even though, in terms of that absolute variation in heights, we're really looking at something that is really quite broad. Now, I said there was a simple relationship between dispersity and standard deviation. And in fact, the dispersity is equal to 1 plus the ratio of the standard deviation to the mean squared. And that ratio of standard deviation to the mean is also known as the relative standard deviation. So we can go quite easily from a figure for a dispersity to a relative standard deviation. And for example, in the case of a dispersity of 1.01, we can see that the relative standard deviation is going to be 10%. Now that means that if we have a polymer with a degree of polymerization of 100 and a dispersity of 1.01, although we might think that this is essentially a uniform polymer, in fact, around 70% of the chains are going to be somewhere between 90 and 110 in terms of degree of polymerization, and around 30% of the chains are going to be even outside of that range. So in absolute terms, we're still talking about a relatively broad dispersity. So this is why I would suggest that at least when we're talking about low dispersity polymers, where the weight average molecular weight is of the same order of magnitude as the number average molecular weight, standard deviation is probably a more useful, more intuitive measure of dispersion than dispersity. And so instead of writing our polymer structures like this with a average degree of polymerization and a dispersity, we should maybe think about adding in the standard deviation. So this polymer, the degree of polymerization of 100, dispersity of 1.1, has a standard deviation of 32. So when we write it like that, we know immediately that most of the chains are going to be somewhere between 70 and 130 units in length. Now, if we want to go a bit further, we can look at what molecular weight distributions really look like. So to do that, we first need to remember that there are different kinds of distribution. We have, when we analyze a polymer, we might run it through a GPC, and we'll obtain a GPC trace, which might be a DRI trace, which tells us what is the mass of polymer that's leaving the system or passing through the detector for a given elution volume. And then we're going to convert that using either a calibration curve or using an absolute mass detector, such as multi-angle light scattering, into a weight distribution. So we're showing the mass of polymer as a function of the logarithm of the molecular weight of the degree of polymerization. Then if we're interested in the number of chains rather than just the mass of polymer overall, we can convert that into a number distribution. And to do that, we're going to divide each point here by the molecular weight at that point. That has the effect of diminishing the high molecular weight region and amplifying the low molecular weight region of the distribution. But we're still looking at a log scale. So then if we want to convert that to a linear scale, we'll go to a number distribution on a linear scale, and you see immediately that there's this enormous change in the shape of the distribution that comes from squashing down this region into a much smaller area and really spreading out the higher molecular weight region as we pass from that logarithmic to the linear scale. Now, if we look at a conventional chain polymerization, that's a polymerization where each chain grows rapidly from an initiator molecule and terminates irreversibly under conditions where we have essentially a constant monomer concentration, so say we're stopping at a low conversion, and where there's a constant radical concentration. We know that essentially the chance the chain terminates or propagates is always constant, and we're going to end up with what's known as a geometric distribution of polymer chains. This is also known as the most probable distribution because it's the distribution that has the highest entropy. And this distribution is characterized by many short chains and then a relatively small number of long chains, which really have a huge effect on the weight average molecular weight or degree of polymerization. And the dispersity of this polymerization is going to be 2. Now, we can see that this produces a very, very broad distribution of chains when we look at it as a number distribution. When we look at it on a logarithmic scale, so the kinds of molecular weight distributions we're used to seeing, this all gets kind of squashed up, these long chains get squashed together, and we end up looking at something that looks a lot more Gaussian in shape. So what you see here is that the GPC trace that we produce is quite different to the number distribution on a linear scale, which is what we sort of think of intuitively when we think about distributions. If we pass to living polymerization now, we're in a situation where all the chains grow throughout the reaction and monomers add individually and independently to the growing chains. So all the chains grow at more or less the same rate. They all end up with more or less the same molecular weight at the end of the reaction. And it was shown by P.J. Flory back in the 1940s that under these kinds of ideal conditions, we're going to end up with a Poisson distribution. And this is really as good as it can get in a chain polymerization. Now, Poisson distributions are characterized by low dispersities. The dispersity is going to be equal to 1 plus 1 over the number average degree of polymerization. But although the dispersity is low, the standard deviation can still be relatively large. So in this case of a polymer with a degree of polymerization of 20, a dispersity of 1.05, the standard deviation is nearly 5. So that's nearly 25% of the number average degree of polymerization. And you can see that the kinds of chains that we might encounter range in size from around about 10 to nearly 20. So there's really a relatively large variation in chain length, even though the dispersity is very small. Now, looking at the case of reversible deactivation radical polymerization, such as raft polymerization or RDRP or nitroxide-mediated polymerization, now we have a system where you have a series of activation and deactivation cycles with active chain in equilibrium with dormant chains, whether that's happening through a reversible chain transfer, as in the case of a raft polymerization, or through a reversible termination in the case of RDRP or nitroxide-mediated polymerization. And during each of these activation-deactivation cycles, there'll be an addition of a variable number of monomer units. And these monomer units are actually added with a distribution which is the same as what you get in an uncontrolled polymerization. You have a geometric distribution of monomer units added in each cycle of activation and deactivation. So that's a very skewed distribution, again characterized by a large number of small numbers of units and a small number of large numbers of units. And what really controls the dispersity in the reversible deactivation radical polymerization is, on the one hand, the number of times that these activation deactivation cycles take place, and secondly, the number of monomers that are added on average in each of these activation deactivation cycles. The smaller that number of monomers and the more cycles take place, the smaller the dispersity will be. And what controls the average number of monomers per cycle is really the rate at which the chains deactivate. So this Kd multiplied by the concentration of deactivator, or the rate of chain transfer in the case of a RAF polymerization, reversible chain transfer polymerization. And it's possible to show that under idealized conditions with no termination or side reactions, as we approach 100% conversion, we'll approach a negative binomial distribution, which is really one of the fundamental distributions of statistics. And it's quite easy to treat mathematically. And so here you can see an example of a RDRP polymerization with, again, degree of polymerization of 20. Now we're using a control agent with a chain transfer constant of 10. We get a dispersity that's still relatively narrow, 1.15, because now the dispersity is given by 1 plus 1 over the degree of polymerization plus 1 over the chain transfer constant at 100% conversion. But again, we have really a relatively broad distribution, even though the dispersity is quite narrow. The standard deviation of this distribution is nearly 8, so it's roughly 40% of the number average degree of polymerization. Now, one of the main motivations for doing controlled polymerizations is to make block copolymers. So what happens when we put two blocks together? So here we've got two blocks, each of which has a degree of polymerization of 20, dispersity of 1.05, a standard deviation of roughly 4.5. We put them together, and of course we make a polymer that now has a degree of polymerization of 40. But interestingly, the dispersity decreases. We've gone from 1.05 down to 1.025. So if we look at the molecular weight distribution on the logarithmic scale, we can see that the distribution of the block copolymer is substantially narrower. At the same time, the absolute standard deviation has increased, and we've passed from about 4.5 to now about 6.3. So it's still relatively small compared to the degree of polymerization, but it's bigger than it was. And this is something that we expect to see in essentially every block copolymerization. And it just comes from the maths of adding independent random variables. If you have two random variables that are not correlated with each other, so there's no tendency for long polymers to add to long polymers, or short ones to add to short ones, or vice versa, then what we expect is that as we add more and more blocks with the same distribution, the standard deviation will increase in proportion to the square root of the number of blocks, but the dispersity is going to decrease asymptotically towards 1. And so even if our initial dispersity is really high, let's say initial dispersity of 2, by the time we've added 10 blocks to our multi-block copolymer, we should get down to a dispersity of around 1.1. Now, that's the theory. In practice, it doesn't always work that way. In fact, it very rarely works that way. So here's an example of a polymerization from the Harrisson group. It was published in 2017. It's a polymerization of butyl methacrylate, and you can see that it is very well controlled. So we have 20 chain extensions, and throughout we're seeing this very clean increase in molecular weight, very nice monomodal chain length distributions, relatively narrow, very good agreement between number average molecular weight and the theoretical molecular weight. And we do initially see a decrease in the dispersity as expected. But then that reaches a plateau at about 1.14, 1.15, and even starts to gradually increase as we get towards the end of the reaction. And if we just zoom in, we can like zoom in on just one of those activation chain extension cycles and try and see what's going on that sort of molecular level, the level of individual chains. So let's start with the polymer on the 14th cycle. It has a molecular weight of 21,500 and dispersity of 1.14. And we're going to take that by adding a block of 1,500 units in length. We're going to get to a polymer with a mass of 23,000 and dispersity of 1.15. And the question is, what are the characteristics of the block that we need to make that transition? And we can work that out. So we know already that the length of the block on average is just the difference in lengths, is 1,500. And the standard deviation we can work out using just the statistical formula for addition of two random variables. We know that the standard deviation of the sum of the two polymers squared is going to be equal to the sum of squares of the standard deviation of that first polymer plus the standard deviation of the added polymer. And when we do that calculation, we find that the standard deviation of the added polymer is almost 4,000. So that's more than twice the number average molecular weight of the added block. And if we convert that back into a dispersity, we have a dispersity of 7.5 and just a very, very broad molecular weight distribution. And in fact, half of the chains in this distribution are so small that you can't even see them. They're effectively not there at all. And so this suggests that although the GPC is telling us that our polymerization is very well controlled, that we're getting a nice smooth increase in molecular weights, on the level of individual blocks, there must be something else going on, that in the sense that we have apparently very large dispersities. And this is not just an issue with that one particular polymerization. As I said, this is really a very well-controlled polymerization. And we see that in essentially all block copolymerizations. Typically, the chain extended blocks appear to have unusually high dispersities. And really why that is, I think, is still an open question. I mean, it could be that we're just not very good at measuring dispersity. Because as you would know, if you've ever treated a GPC, dispersity is very sensitive to changes in the baseline or changes in peak selection. And these things can all have a very big effect on the number average molecular weight, which then has an effect on the dispersity. So we need to really take these dispersity figures with a grain of salt. It could also be because of the formation of dead polymer chains. But this suggests that we're perhaps getting quite a large number of dead polymer chains in these polymerizations. And finally, there could also be some chain length effects on chain deactivation. Perhaps longer polymers are just less good at getting deactivated than shorter polymers. So as I said, this remains an open question. Now, I'd like to just pass on now to composition distributions, since we're talking about multi-block copolymers. So in addition to molecular weight distributions, we also have the issue of composition distributions. So if we were to take this hypothetical example of a 12-block copolymer consisting of these repeating sequences of short block of monomer A, B, C, D, A, B, C, D, A, B, C, D. Each block being 3 units long on average, and we're working in ideal conditions. So we're going to select the block lengths from a Poisson distribution with average length of 3. So we can see our target structure. If we then try and simulate that, what are we going to get? So we're going to start drawing blocks at random. Our first block is 2 units long. Then we have one that's 5 units long, 6 units, 5 units, 3 units, 3 units, 1 unit. And then there's a 5% chance that we're going to get a block length of 0. And that's actually happened here. So we're going to have a missing block and then continuing until we get to the end of the polymer chain. And what we see is that by the time we've added together 12 of these blocks, we end up very close to our target molecular weight. We've only overshot it by 2. But on the level of individual blocks, there's really quite a lot of variation. We have blocks that are as long as 6 units long, and we have blocks that are not there at all. And we can simulate a number of chains. What we're going to find is that in terms of the number of chains which have all of the blocks, there's actually quite a large number that are missing at least one block. In fact, we can calculate that with a 5% chance of missing a single block, then when we add 12 blocks together, we're going to go up to 46% of chains that are going to be missing at least one block in this system. And that's an issue that can be alleviated by pushing towards larger blocks. And so we recommend at least six monomer units per block. But I mean, the more the better, really, if you want to try and be certain that you're going to get the majority of your structures having the order of blocks and sequence of blocks that you want. We can also then look at the distribution of individual monomers within each block. So for instance, looking at how monomer A is distributed across the whole polymer, and we can generate probabilities as a function of the position in the chain for this monomer. And so what we can see is that at the beginning of the chain, we have a very high probability of finding monomer A. And as we go through, that decreases. So by the time we get to about the 6th unit in the chain, we have a very low but non-zero probability of finding monomer A there. And it rises up a bit, but we never really get to a very high probability. And basically everything just flattens out. So we start to lose that long-range order. We can do that for each of the monomers. And what we see is that basically just because of that random variation in the length of individual blocks, we quickly lose that long-range order. Now, that loss of order, in some senses, can be an advantage. And so I want to just finish with an application in self-assembly using gradient copolymers. So why are we interested in gradient copolymers? Well, the main reason that our group was interested in looking at them is because of their properties in dispersed systems. So whereas an amphiphilic block copolymer in a selective solvent is going to form micelles or other aggregates, those aggregates are typically frozen. They don't interchange with each other, and as a result, they're not very good at responding to changes in their environment. But it's been shown by a number of researchers that gradient copolymers can form dynamic assemblies in a selective solvent that are at equilibrium with each other and then thus able to respond in a reversible manner to changes in their environment. And they can change in terms of their size, and they can also change in terms of their morphology. Now, a gradient copolymer is simply a copolymer whose composition varies as a function of chain length. So in this simple case of a linear gradient copolymer, we're going to pass from 100% monomer A to 100% monomer B. But that simple picture runs into a problem straight away, because you can't ever have, in the sense of a single chain, you can never have a position in a single chain that is 30% monomer A and 70% monomer B. It's a discrete system which is either one or the other. And so when you try to simulate a gradient copolymer, we see that, yes, we find that we have at one end all monomer A, at the other end all monomer B, and in the middle there's sort of this transition from one to the other, but there's just an enormous amount of variation from one chain to another. And if we were to take one single chain, we couldn't reconstruct the overall composition gradient. That composition gradient is really just a property of the whole aggregate of chains together. And so we were interested to see, well, to what extent does this random variation smooth things out? And so we were interested in particular in comparing a linear gradient copolymer with this smooth variation in composition from one end of the chain to the other, and a very simple stepwise gradient copolymer, which is essentially just a diblock copolymer containing one block which is enriched in monomer A and a second block which is depleted in monomer A. And if we run just a simple simulation of these polymers, you can see that the distribution of monomers within each polymer chain is very similar in both cases, just as a result of the random variation that's inherent in the polymerization process. And so we set about preparing polymers with a linear gradient first, starting with acrylic acid as a hydrophilic pH-sensitive monomer and butyl acrylate as a hydrophobic monomer. And we did that using quite a complicated semi-batch setup with 2 syringe pumps, adding the different monomers at different rates and trying to maintain the appropriate concentration of each reagent as the polymerization proceeded in order to get that nice linear gradient while maintaining control of the polymerization. As you can imagine, that was quite a difficult process with relatively poor reproducibility, and it took us a long time to get some nice linear gradient copolymers that we were happy with. On the other hand, the asymmetric diblock copolymer could be produced in a very simple process using stepwise synthesis. And this was something that we could actually do using a robotic synthesizer in the laboratories of Professor Uri Schubert at the Jena Center for Soft Matter. And so we were interested in how these polymers behaved in terms of their self-assembly. We first looked at block copolymers, acrylic acid and butyl acrylate, and we saw, as expected, that while they formed aggregates in solutions of high pH, they really show very little responsiveness to changes in pH. As the acrylic acid got protonated, the blocks were frozen. They weren't really able to do anything until they just became insoluble and precipitated at around pH 4. On the other hand, our gradient copolymers started off forming very small aggregates. As we changed the pH and the acrylic acid got protonated, became less soluble, they formed larger aggregates, and this was a reversible transition, and they got back to the same place, suggesting that these assemblies really are at thermodynamic equilibrium. And something that was interesting was that our diblock copolymers here, our asymmetric diblock copolymers, showed the same kind of behavior, starting out small, getting larger, and then coming back to where they were. So it's very similar behavior to the gradient polymers. And we also saw changes in morphology that were, again, very similar between the two types of polymers. So gradient copolymers passed from initially slightly elongated spherical particles through to worms at around pH 7 to pH 5, and then to a mixture of worms and vesicles, while our diblock copolymers showed similar types of behavior, again passing through these transitions of spherical to worm-like to vesicle type morphologies. So to wrap up, what I hope I've shown is that polymer molecular weight distributions are much broader than we imagine, and control over monomer placement in precision chain polymerization is quite limited because of the breadth of these distributions, even in very well-controlled polymerizations. And so this is because the average structures that we draw and the GPC traces that we see can hide an enormous amount of variation in them. If you want to visualize that variation, just making some simple statistical models and simulating a few polymer chains, drawing them out, can be extremely useful in order to give you a picture of what kind of distribution you have in your system. And then what I hope I've shown with that very last part is that simple synthetic models can be good mimics of more complex composition profiles. Again, because of the random variation, which means we lose a lot of the detail of changes in composition profiles. And so with that, I'd like to thank my co-workers, particularly Barbara Frias-Mencia and Junliang Zhang, who worked on those gradient copolymer results that I showed at the end. and also my co-workers in Toulouse in France, and Matthias Desterac, Barbara Lanetti, my collaborators at the Jena Center of Soft Matter, Ulrich Schubert, Carlos Guerrero Sanchez, and also at Warwick University with Sébastien Perrier and Guillaume Gaudy when he was a postdoc there, the UNSW, Buzz Edlund, and the funding agencies, and thank you for your attention.